Hi guys, and welcome to this second part of chapter 40. This deals mainly with basically doing problems from this chapter 40. There was an item from the lecture that I forgot to mention, and that was basically when we arrived at the standing waves for a particle in an infinite well. If you guys remember, we came up with this expression at the end for psi as a function of x and t actually as some constant, which I call that c times sine of kx exponential basically, or negative I e t over h bar. Basically this is the result for a particle set that box, where basically k in this case was related to namely k times l is equal to n pi, which means that k is equal to n pi over l. Okay, that was the box of with basically L. From 0 to L, the particle can only exist in this region, and the well is infinite. So this is the case of the infinite well. Okay, I promised during that time that we will go back and revisit what this C is, and it has to do with the normalization. It has to do with the fact that we know the particle has to be between 0 and L. So, and this is basically the interpretation for the this wave function. So what we're saying in this case is the probability of finding this particle, namely psi squared basically dx. If I add up this quantity from negative infinity to positive infinity, that is basically what that means, it's equal to 1. However, we know that psi is equal to 0 everywhere except between 0 and L. And so this integral really is the integral between 0 and L of this function. And this function, if you can clearly see, is it has a real part in here. So I mean sine kx is real. The exponential now here is an imaginary. So if I take its complex conjugate, I will end up with an exponential of plus i.e. h bar t. I mean i.e. t over h bar. So if I basically complex conjugate that, so it's going to give me just 1 basically. So let's write it down. So it's going to be c squared. First of all, I'm going to take c squared real because there is no need for it to be complex. And if it is, then we're going to put it between its absolute value too. We're going to get the modulus of that. So the sine times sine is going to be sine squared, but again the exponential of minus ikx times the exponential of plus ikx, because this product actually is psi times psi star. Okay. And the only place where it can basically, where we have a complex number in here, is in the time component, and the time component t, I'm sorry. Why is it k? It's e over h. E t over h bar. Anyway, it's going to become 1, so that's why I really am not worried too much about it. So this whole thing means that we know for sure that the particle exists between 0 and L. So this is the so-called normalization. Okay. So from here, it's a condition basically on C. From here, we have an equation for C basically. So that means that C squared times the integral from 0 to L of sine squared at the end, kx, integrated between 0 and L is equal to 1. Well, obviously, I'm going to write this one in terms of L quickly and use a trig identity. So it's going to be c squared, the integral from 0 to L of sine of n pi times x over L squared dx is equal to 1. Okay, so because we know that this particle must exist between 0 and L, that's why we're sure, 100% sure. Because this by itself is the probability density function, I mean psi itself squared. So if we add all of these probabilities, we will get 1. So let's do this integral. For that, we're going to do the following. Okay, we note that cos squared minus sin squared is actually equal to cos of twice the angle. So it doesn't matter what the angle in there is. Okay, so from here we use the other identity that tells me that cos squared plus sin squared is equal to 1. To get rid of that sin squared, then I have basically this identity, meaning that the sine squared of anything is equal to 1 minus cosine of twice the argument of the angle divided by 2. So I'm going to sub that expression in there so that we can integrate. So what we have in this case is we have c squared, the integral from 0 to L of 1 minus cosine. I have 2n pi x over L divided by 2 integrated over dx equal to 1. I know we did this expression a lot of times. We worked with this when we were doing basically the root mean square for in the kinetic theory of gases, or when we did actually the also another expression for the root mean square. It came in electricity, it came in a lot of places. Okay, so this integral is a common integral. Now this integral has the integral of 1/2, which is just going to give me the integral of 1/2 between 0 and L, minus the other integral, which is c squared again over 2, the integral between 0 and L of cosine of 2n pi x over L dx. This must be equal to 0. I mean equal to 1. I'm sorry. So now this integral of a cosine with a negative sign is positive, so all I have to do is multiply by L and divide it by 2n pi, but then I'm going to end up with a sign. So the part, first of all, it's going to be 1/2 of c squared times L minus, again, L over 2n pi times c squared over 2 times a sine of 2n, so it's going to be a positive now. No, it's going to stay negative. Sorry about that. 2n pi x over L evaluated between 0 and L. So this whole thing equal to 1, but this one part is actually equal to 0. The reason being is because sine for x equal to L, I have L over L, so I'll have sine of 2n pi. No matter what, it's going to be 0. Sine of 1 pi or 2 pi or 3 pi, but actually here the even numbers. So sine of 0 or sine of 2 pi or sine of 4 pi, they are all 0, and sine of 0 is 0. So both the upper limit and the lower limit are 0. From here, I have an equation for basically c that is going to be equal to square root of 2 over L, basically. Okay, because this whole thing is equal to 1. So that is basically how we find the value of c. And from here, now we have the stationary modes for this wave equation for the particle inside an infinite well. You can write them now normalized as being basically square root of 2 over L sine of n pi x over L times exponential of minus e. Actually, we have the energy levels in this case, En times T over h bar, and this is the so-called the stationary values where we know that the particle, and you can go and revisit back what this En is. It has to do with n squared times the energy levels. What is it? N squared times h bar squared pi squared over 2ml squared. So again, this is the stuff we have seen in the lecture, and this is just something I promised in the lecture and didn't finish. So let's get going to the problems. So the first problem we're going to be doing is problem 28, and from problem 28, and the reason why I thought we should do it is because I forgot to mention an expression that is heavily used in there, and of course the derivation for it is kind of hard, but the formula for it, and that is the probability basically of a particle going through the barrier, the potential barrier. If you look at the expression for it is basically called, for the tunneling probability T, this expression is needed for that, which is 16. I mean, it really is basically, how should I put it? Let's put it first of all in general formula. It's equal to G times E to the negative 2. Don't forget the 2, because that 2 will throw you off completely. Kappa L, where L is actually the width of the barrier. Okay, and G is equal to 16 times the ratio of the energy, the kinetic energy of the particle divided by the barrier itself, U naught or V naught. 1 minus the same thing, E divided by this U naught. Obviously, if you have an energy almost equal to, so this is U naught, you're going to make the barrier easier. You're going to pass it easier. But if you come in here, it's going to be harder and harder. So this tunneling probability will be less. So this is the tunneling probability. How likely is a particle going to tunnel through this barrier, basically, tunneling probability. Now, kappa itself also is related to the energy gap between these two numbers. So it's going to be related to, is going to be equal to the square root of the 2 mass of the particle times the difference between, again, the potential maximum in this case minus E divided by h bar. Okay, so this is basically the expression that you're going to be using for this one, where L is actually the gap between that. So problem 28. Problem 28 says basically an alpha decay in a simple model of a radioactive nucleus, an alpha particle, and they give you the mass of the particle because we will need it for kappa in here. So the mass of the particle. So the more heavier the particle it is, the less this probability is, because this number is going to be more. So the lighter the particle, the more capable it is going to pass through this barrier. So again, the alpha particle, the mass for it is given in this problem as being 6.64 times 10 to the negative 27 kilograms. So this is the mass of the alpha particle. It's trapped by a square barrier that has width of 2 femtometer. So basically in this case, L is equal to 2 Fm, or 2 times 10 to the negative 15 meters. Okay? And a height of 30 mega electron volt. So U naught is equal to 30 mega electron volt. Okay? And they tell you what is the tunneling probability when the alpha particles encounter the barrier if the kinetic energy is 1 mega electron volt below the top of the barrier. So it comes just 1 meg short. So it comes with 29 meg basically. Whereas this is a 30 meg barrier. Okay, so we want to find basically T. So for that, again, we're going to find G, and we're going to find kappa, and we're going to use the formula to find the probability. So G, first of all, it's 16 times, in this case you don't really need to convert anything with anything, just leave them everything the way. So we know the energy is 29 divided by 30 times 1 minus 29 divided by 30. So this number is going to be a number. Let me put the calculator quickly in here. I trust that you guys are going to do the calculations with me too. So I did these calculations earlier too. So I have 16 times 29 times open parentheses 1 minus 29 over 30, close the parentheses, and then divide the whole thing by 30 again. So basically this number is 0.5 1, and then repeating 5s. Okay, this is G, and we want kappa also. Kappa for this particle is going to be equal to the square root of 2 times the mass, which is 6.64, times 10 to the negative 27, times the difference in energy. The difference in energy, they tell you it's 1 short, so we know it's 1 meg, times 10 to the power 6 mega electron volt. So we need to convert this one to joules. So this is how many joules that 1 meg, the difference, the gap basically. And then times what else do we need in here for kappa? That's it, divided by h bar. Yeah, we divided by h bar. Okay, since I really don't memorize h bar, I should. I know what h is, which is 6.26 times 10 to the negative 34, and then I have to multiply in here by 2 pi. So let me plug this number in here to find kappa. It's going to be a big number, okay, because of this 10 to the negative 34. Although you have a square root of 10 to the negative 27 and negative 19, that's negative 46. So that is going to be 10 to the power, what is it, 46? When you divide that by 2, so it's going to be 10 to the negative 24. But no, I'm sorry, 23, and 10 to the negative 23, don't forget you have in here 10 to the power negative 34. When you take it upstairs, it's going to be a lot of numbers. So let's see how that is. Okay, it's going to be 2 times pi times square root of open parentheses of 2 times the mass, which is 6.64, times the power 10 to the negative 27, okay, times, oh man, I have a 10 to the power 6 too, so this is going to make it even a bigger number than what I was thinking in here. So it's going to be 10 to the power 6, that's coming from the mega electron volt, and then times the electron charge, in this case 10 to the negative 19. Okay, close this whole thing under the square root, divide by open parentheses 6.626 10 to the negative 34. Okay, so it's a big number as I expected. Kappa is equal to 4.374. 737. So you guys are supposed to do these numbers anyway. 10 to the positive 14. Okay, SI, because we used everything in SI. So the length now better be in meters if we're going to expect to find this expression. So T now. T is going to be basically G times exponential of minus 2 kappa L, which is G. G is equal to 0.5516, okay, times this exponential of negative 2 times this number 4.374 times 10 to the power 14 times 2 times 10 to the negative 15, okay, because L is 2 femtometers. So if I plug in the numbers in here for T, the probability that this basically alpha particle will decay according to this model, so it's going to be E, no, first of all, the number, okay, so I'm going to use the exact number, I mean not the exact number, whatever this calculator gave me, so it's I really should use sig figs, but E to the power, open parentheses, negative 2 times this number, come on, okay, times 2 10 to the negative 15. Close the parentheses and let's hope everything is correct, and the answer is 0.0896, or basically 8.96%. So this is how much probability that basically that this particle will make it across to the other end, having 29 mega electron volt, 1 mega electron volt short of the gap, basically, to make this basically decay. Okay, it needs 30 to actually make it easily, but that's another issue. Anyway, part B, what is the tunneling probability of the energy of the alpha particle is 10 meg below the top of the barrier. Now it's here, not 1 meg below, it's 10 meg below, so basically it's 20 meg electron volt. So obviously the probability should be less now. By how much? So I'm going to recalculate G again. G now is going to be equal again 16 times the energy, which is 20 now, over 30 times 1 minus 20 over 30. So G now is going to be equal to 16. Okay, can I use the formula and just change the numbers in here? Yeah, okay. So the energy now is 20, not 29. And the other term also is 20, not 29. So this is giving me 3.5 repeating. So here, G has increased, okay, from 0.5 to about factor of, what is it, 7? Let's see what happened to kappa now. Kappa now is equal to the square root of, again, of 2 times the mass of the alpha particle, which is still 6.64 times 10 to the negative 27, times the gap in the energy. Now it's no longer 1 mega electron volt, but it's 10 mega electron volt. So this is what's going to make the difference in here. As far as this term, it increased. So this is, instead of dividing by square root of 1, now you're dividing by square root of 3. So, square root of 10, which is going to be a 3, so it's going to be in e to the power 3. Negative 3, that is. Okay? times again 1.602 times 10 to the negative 19. So this is basically the expression, and the whole thing is divided by each bar, which is 6.626 times 10 to the negative 34, but you have a 2 pi in here, because that is actually h and not h bar. Okay, so if I use that formula now for kappa, so it's the same formula as before, with the exception now the energy gap has increased by a factor of 10 now. It's no longer 1 meg, but it's rather 10 meg. So in this case, this number now has increased by almost a factor of 10. Or if I don't know, it's 1.38 3 times 10 to the power 15, again in SI units. I think it's 1 over meter. Okay, to use everything correctly. So now T for this case, again, it's going to be this new G now, which is 3.5 repeating, times the exponential of negative 2 times this number, which is 1.383 times 10 to the power 15, times 2 times 10 to the negative 15. From the get-go, these two numbers cancel, and you basically have a negative 4 times. So let's come back to this expression again. And find it. So where is the 3.5 repeating? Times exponential of, open parentheses, negative 2 times this number, times 2 now, times 10 to the power negative 15. Close the parentheses. So it's giving me 0.0141 or 1.41%. In other words, probability went down, okay, as expected. The probability of the decay went from almost 9% down to a little over almost 1.5%. And that is expected because now the energy gap is bigger. So it's less tunneling for a particle that is 10 meg short of the barrier, short of the peak of the barrier, than one that is just 1 meg. Okay, so 10 meg requires, it's very unlikely, relatively speaking, compared to the other one. Okay, so that is basically the alpha decay modeled with this tunneling expression here. There are a lot of problems in here that involve tunneling, and hopefully you guys can go through them and should not have any difficulty. Problem 35, that's the next problem that I promise we'll do. Okay, so this was problem 28. Problem 35. For problem 35, it says chemists use infrared absorption spectra to identify chemicals in a sample. In one sample, a chemist finds that that light of wavelength lambda equals to 5.8 micrometer. I mean, I know they call it light, 5.8 micrometer. But this is a very, very, very long wavelength. Yeah, it's an infrared. Okay, so it's not really light. Okay. Okay, so let's muse them and call it light. Okay, it's an infrared. Because light usually is a much shorter wavelength than this one. So when a molecule makes a transition from its ground harmonic oscillator level to its first excited level, find the energy of this transition. Well, since they gave us the wavelength, then we know the energy is just E is just h bar omega, or it's hf, and f is equal to the dispersion law. Remember, the speed of light, c, is equal to lambda f. Since they gave us lambda, we can express f as being basically c over lambda. So this expression just becomes equal to, what's the question? Just make sure we find the energy of this transition, because this transition gave us this wavelength, so we know exactly what this energy is. So then it's equal. So you see, it's when you plug in the stuff, it's just simple stuff. When you 6.26 times 10 to the negative 34 times the speed of light, which is 3.8 3 times 10 to the power 8 divided by lambda, which is 5.8 times 10 to the negative 6. That's what a micro is. Usually we express this number in electron volts, so it's a, I mean, if we do this one, we're going to get it in joules, but usually we express it in electron volts. So divide by 1.602 times 10 to the negative 19. Okay, so that is, did they say to use it in electron volt or not? No, they did not. Typically use the electron volt for this kind of problems. Okay, that's how they communicate the energy in this point. So 6.626 10 to the negative 34, because it gives us a nicer number than some power which is to the negative something. Okay, much easier to say this many electron volts. 10 to the power 8 divided by, open parentheses, the wavelength 5.8 10 to the negative 6. This is going to be low energy, 1.602 10 to the negative 19, and this whole thing is 0.21 electron volt. I mean, the wavelength is very, I mean, infrared doesn't have much energy in it anyway. So electron volt. So as expected, this number is tiny. Okay. So we have the wavelength, we have the energy. If the molecule can be treated as a harmonic oscillator with mass equal to 5.6 10 to the negative 26 kilograms. So if the molecule, so what kind of molecule is that? So we have a proton 1.67. I'm just trying to think in here what kind of molecule they have in mind. 5.6 divided by 1.6 or 1.7 roughly. So this is a little over 3, so it's not, it's probably an H2, it doesn't matter. Okay, it doesn't matter. So what type? So it's a little over 3, maybe 3.5 for protons in it. Okay, so part B now. Maybe it's helium. Okay, if the molecule can be treated at, which is a monoatomic gas anyway, so it's probably that. So if the atom can be, so we have the mass now m. Find the force constant. So basically, since we know what the frequency is, the frequency, remember, is equal to c over lambda, and that means omega is equal to 2 pi f, which is 2 pi c over lambda. And now we have omega is approximating it to a harmonic oscillator k prime over m. We use k prime in this class for the spring constant because of the fact we have k everywhere for the wavelength, so we don't want this to get confused. So from here we're going to get the spring constant k prime equals to basically m times 4 pi squared c squared divided by lambda squared. So the mass is 5.6 times 10 to the negative 26 kilogram times 4 times pi squared times 3 times 10 to the power 8 squared, and the whole thing is divided by the wavelength squared, which is 5.8 times 10 to the negative 6 squared. Let's see what this k prime turned out to be. It's going to be an SI, it's going to be in Newton per meter. Okay, that is because in the spring constant F equals to kx. Obviously I'm worried about the negative, so this is k prime, so it's going to be Newton per meter at the units because everything is in SI. So it's going to be, what is it? The mass is 5.6 10 to the negative 27 26. Oh man, I'm sorry, I made it's 32. So 16, so it must be an oxygen. It must be an O2. So earlier when I divided by 10 to the negative 7, so this has about 32 protons, basically, the mass of 32 proton. So this gas is they're talking about is some oxygen gas, basically, O2. Okay. So again, you need to pay attention to your numbers. So it's 10 to the negative 26. So when I was putting it in here, I realized that I put the wrong unit in there to estimate what kind of molecule is this one. Pi squared. Okay. Times open parentheses 3 10 to the power 8 squared divided by open parentheses 5.8 10 to the negative 6, and the whole thing is again squared in the denominator as far as the wavelength is concerned. So this is 5,914 newtons. Obviously, we have to be careful about this business of sig figs, but it's 5,915 Newton per meter. Okay, this is a very, 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 very sturdy spring. Okay, this is a spring that you use probably for trains. Imagine that. Okay, so this is problem 35. Kind of nice, isn't it? This basically ties into the harmonic oscillator. There are a bunch of problems in here with the harmonic oscillator, so you really need to remember that stuff for its energy. So problem 41. Okay, for problem 41, basically what they say, they gave us the particle of mass m in a one-dimensional box has the following wave function in the region between 0 and L. So they gave you the wave function, a combination of two stationary states basically, and both of them are and it's normalized, so the functions psi of x and psi 3 of x are the normalized stationary state wave functions, and for n equals to 1 and n equals to 3 levels. So, and A1 and E3 are the energies of these levels. So we have everything for this one. The wave function is 0 for x less than 0 and for x greater than L. Find the value of the probability distribution at x equals to L over 2 as a function of time. Okay, so let's write this thing in here. Okay, so we have psi of x and t. Okay, the big one, not just the spatial one, is equal to 1 over square root of 2 times psi 1 of x exponential of negative I e1 of e1t over h bar plus 1 over square root of 2 psi 2 of x exponential of negative I e3, no, this is 3, I'm sorry, e3t over h bar. Okay, so this is the function that they gave us. Since this is a harmonic oscillator, I know exactly what psi 1 is, and I know exactly what psi 2 is. Not a harmonic oscillator, I'm saying a particle in a box, okay? Okay, so we know that psi 1 of x is equal to basically, what is it, 2 over square root of L sine of n, which is 1 pi x over L, and also psi 3 of x is equal to square root of 2 over L times sine of 3 pi x over L. This is, we know it, and as a matter of fact we know the values of E1 and E2 actually too. E1 is equal to n squared times this number, and E2 is 3 squared, so let's copy this expression here, n squared h bar squared pi squared over 2ml squared. Okay, so it's 1 squared times h bar squared, what is it, pi squared over 2ml squared. Okay, again, just in case, h bar squared pi squared over 2ml squared. Okay, now E3 on the other hand, it's basically 3 squared, which is 9, times the same stuff, h squared pi squared over 2ml squared. Okay, so we have everything for this particle now. We have its wave function, combination of these two stationary states. Okay, and the energies of these levels, the wave function. Find the value of the probability distribution function at x equals to L over 2. So we're gonna find, so for L equals to 2, x equals to L over 2, we know what psi 1 is. We know it's equal to square root of 2 over L times sine of pi times, basically, look at this number in here. X is L over 2 and divided by L. Don't forget that L. So this is actually nothing but square root of 2 over L, because sine of pi over 2 is just 1. Okay. Psi 2 then, at that point, we're looking at this specific point in space. Okay. Psi 3, I'm sorry, is equal to square root of 2 over L, the same thing except sine of 3 times pi times, I wrote the 3 already. No, it's not correct. Okay. So it's L over, yeah, it's 3, because we have an n in here, which is 3 pi, times L over 2 also divided by 2. Divided by L, cancel the L. So this is actually negative. Sine of 3 pi over 2 is a negative 1. So this is going to be square root of 2 over L with a negative sign, that's all. So we have these two functions. So all we have to do is write the function psi now in the point L over 2, and time t is going to be equal to 1 over square root of 2 times square root of 2 over L exponential of negative this stuff times t. So I'm going to leave it e1, okay, because it's going to be cumbersome to write it, but at the end we're going to sub the values. Okay, so it's going to be negative I e1 t over h bar plus or minus now 1 over square root of 2, and square root of 2 is actually given in here, times the square root of 2L over L times the exponential of negative I e3 t over h bar. Okay. Okay, I'm going to call e naught this number, or e1. So this is actually e3. You can clearly see that it's equal to 9 e1. Okay, because if this is just 9, that number. Okay. So psi then is equal to, and this point, of course, L over 2 at any time is going to be 1 over square root of L times the exponential of negative I e1 t over h bar minus 1 over square root of L exponential of negative 9I e1 t over h bar. That is basically how psi looks like in that point. So this is just a reminder. This is not psi everywhere. It's psi at L over 2 at any instant. Okay. We need to form psi times psi squared, psi star. So we need to form psi, the probability itself, squared, which is nothing but psi times psi star. So this is the product of, first of all, I have 1 over L and 1 over L, under the square root becomes just 1 over L. Now, the first term, exponential of negative I e1 t over h bar minus exponential of minus 9 I e1 t over h bar. Remember, e1 is given by that whole big term in here, h bar squared pi squared over 2ml squared. Okay, times the complex conjugate is wherever you see an I, you change its sign. That's all. So now it's going to be an exponential of positive I e1 t over h bar minus exponential of positive 9I e1 t over h bar. The first term times the second term, that is simply equal to 1. The first term times this term will give me e to the 8 IE, because 9 minus 1 is 8. This term times that term is going to give me the exponential of negative 8, because negative 9 plus 1 is 8. And this term times that term, minus times minus is plus, and this term is 1. So here is the result then. It's going to be basically 1 over L times, this is 1, product of the first term. The product of the last two terms is also 1, and it's a positive, okay? It's not negative, because a negative times negative is positive, and these two will give you 1. Now, I'm left with this number in here, which is negative exponential of positive 8 I e1 t over h bar. And then I have on this side too negative exponential of negative 8 I e1 t over h bar. Okay, so these two terms, basically, let me write them as Taylor series. Okay, remember I alpha is equal to cosine alpha, not the Euler expression, I'm sorry, I sine of alpha, and exponential, it's the same angle alpha in here, it's the same argument, with except the I is changed sign, that's all. It's cosine of alpha minus I sine of alpha. So if I add these two numbers, because that's exactly what I'm doing in here, I'm adding them, the sign cancels and I'm just ending with 2 cosine of alpha. So this expression then boils down to the following, that this probability then, distribution function, is given by, first of all, I have a 2 in the first term, 1 over L first, times the 2 minus, again I have a 2 also coming from this summation, 2 cosine of that argument in here, which is 8. Of course, the probability is going to be positive. That's the whole purpose of multiplying by the complex conjugate. I mean, it's not. It's going to be a complete real number, so it's not going to be a. It's going to be positive still too. So it's not going to be a complex number. That's why we don't see any i's at the end. So it's an 8 e1 times what is it again? T over h bar. Okay. If now at this point you can take first of all the 2. And you're in business. So this is equal to 2 over L times 1 minus cosine of 8 E1 T over H bar. Okay, this expression of 1 minus cosine business, if you guys remember from this expression way back when we were doing the normalization for the first term, we encountered it actually. Namely here, 1 minus cosine of twice the argument is equal to basically 2 times the sine squared of that same angle. So basically all we have to do now is divide this by 2 and this becomes a square again. Okay, don't forget we're going to pick up another 2 in here, so it's going to be 4 basically. I mean, okay, this is actually equal to 1 minus 2 times sine squared of half of this angle, which is 4 E1 T over H bar. So that is basically what I'm saying. 1 minus 1 is going to be 0. Minus minus is going to be plus. So I'm going to end up with 4 over L times the sine squared now of 4 E1 T over H bar. Okay. So this is the probability function. And as a matter of fact, we're going to write it down even better now. Since we know E1 is basically E equal to h bar squared pi squared over 2 ml squared. So that means that if I multiply this by 4, I'm going to end up with 4 pi squared, and 4 pi squared h bar squared is h squared. So now, in light of all of that, we can write the expression now as the probability distribution function as 4 over L times the sine squared of and one of the h squared. Oh man, I don't need to do that. Okay, so let's leave it because we're going to cancel one of the h bars in there. So let's leave it 4 pi squared h bar t over 2 ml, and now cancel this 2 when you're in business. Okay, now you are in business. Let's see here. This is finally equal to 4 over L sine squared of now pi times h times t over m times L. Whew. Does it even make sense? H has the units of a joule times second, which is a kilogram times meter per second squared times second times this second, which makes it another second. Divide the whole thing by a kilogram times meter. Oh yeah, the second cancel this second, and the meter cancel. Yeah, it's a dimensionless number as as expected. Well, this is joule times second, and there is another second in here. It's a joule times second squared, and the joule is wait a minute in here. I think I'm missing, oh, distance squared. Yes, we're missing a distance squared. You see here, that is a good place to use the dimensionals, because joule is actually Newton times meter, so we're missing another meter in here. Joule is force times distance. So again, kilogram meter squared per second squared, that is the joule, times the second, which is the unit for the action, in this case for h, times s, which is another second coming from this time, divided by the kilogram times meter squared in here. So everything is all well now, because this meter squared is exactly how it's supposed to be, and the equation is fine. Okay, so dimensionless, the argument of the sign need to have no units in it. So this is the answer to that part of the question. So find the energy level of the transition. Oh, what is the problem? No, we're doing problem 41. I'm sorry. So this problem is problem 41, by the way, okay? Did I write it down somewhere in here? Yeah, problem 41, yes. So we're not doing 35 anymore. Find the value of the probability distribution at x equal L over 2. So it's really just a matter of plugging in the value in here for x and doing basically the stuff that has to do with multiplication and getting stuff everywhere. Find the angular frequency at which the probability distribution oscillates. Obviously, this is an oscillatory function, and it oscillates with this frequency. Okay? I should say it's oscillating actually with this frequency because of the fact that the sine squared itself is a function that goes like this, basically. So it's always positive, so it's 0, and it's going to oscillate. So it's omega actually is half that much. Okay, the period, I'm sorry, is half that much. Okay, since the period is half that much, the value of the oscillation is going to be twice this many. Okay, so omega of oscillations in this case of this probability distribution function is going to be basically 2 pi h over ml squared. Okay, that is basically, it's going up and down periodically, as you can clearly see, and it's always strictly positive. Again, as we said, it has to be positive. It's a probability. It cannot be negative. And the minimum is 0. The maximum is going to be 4 over L in this case. And in that point specifically, so it's fluctuating up and down. And this is the rate at which it's fluctuating. It's actually not this whole thing is omega, but rather it's just this one. This is basically the period t, which is half of this 2 pi over this one. So if you plug in the numbers correctly, you're going to find that this is the correct answer for it. Okay. Anyway, so this is problem 41. Let me take a pause in here quickly, and I will come back and do with you guys problem 44 and problem 60. Those are the two problems that are left in here. Okay. Okay, so let's resume this. So basically now we have problem 44 and problem 60. Actually, I was going to do problem 63, but then I thought about 63 actually is a problem that you guys, if you're going to be majoring in physics, be ready for that, because I avoided explicitly and actually in purpose a different formulation of this quantum mechanics, and usually at this level you avoid it anyway, so it's not really that you're missing much. But down the road, if you're going to be into physics class, into an upper division physics class or even graduate class, you're going to not use this form of Schrödinger equation. You're going to be using basically Dirac algebra, and in Dirac algebra basically Schrödinger's equation will have a completely different form, and we use actually bra in this case to represent the wave function. So it's like a vector basically, and this is like a normal vector, but then if you're forming the product with it, you have to use the ket in this case. So this is like the complex conjugate, and this is your basically the way that the dot product is defined in there, and the differential equation is actually going to be slightly different in here. IH bar, what is it, the operator for E, basically E psi is equal to the Hamiltonian in this case times psi. So I avoided this in purpose, and this is basically what problem 63 deals with. It actually takes something called the commutator. It takes the Hamiltonian in this case, which is for a particle inside a like the harmonic oscillator, I'm sorry, and for it you're going to build your way without actually doing any differential equation whatsoever. You're going to build yourself and find the energy for it. So I avoided problem 63 in purpose because this stuff, if you're going to major in physics, you're going to see it until you get sick of it. But if you're not going to be majoring in physics, you ignore this kind of problems or this approach to quantum mechanics altogether. You stick with this one; it's fine for all purposes, basically. Okay. Anyway, so problem 44. Problem 44 says a particle is in a ground level of a box, extends from x equal to 0 to x equal to L. What is the probability of finding the particle in a region between 0 to L over 4 and L over 4? I know I mentioned that also in the lecture to some extent, that the harmonic oscillator, the case for it is that in quantum mechanics, the particle finds most of its time near the center, basically near the position of equilibrium, whereas in classical mechanics it finds itself most of the time in the edge. So this is an illustration of this point. Although we are not using the harmonic oscillator, this is true almost for all quantum systems. So let's look at this in here. It says calculate this by integrating psi squared dx, where psi is normalized from x equal to 0 to x equal to L over 4. So the particle is in the ground level of a box. So basically we're going to take the n equals to 1. Okay. And we know that this particle then wave function is given by equal to what is it? Did we find square root of 2 over L times the sine of n is 1 in this case, so it's pi x over L exponential of negative I E1 t over h bar, where E1 is exactly that number that we've been dealing with earlier. Okay, this is exactly this number in here, h bar squared pi squared over 2ml squared. Okay. So this is psi for a particle in there. Now we want to find the probability for the particle to be anywhere between 0 and L over 4. So for that we're going to take psi squared dx and sum it up from 0 to L over 4. Okay, psi squared, this exponential again is going to be not there, because you have an exponential of negative IE1 t over h bar, and you multiply it by another one that has a positive EI1 t over h bar when you do the complex conjugate, so this 2 will have an exponential of 0, which is 1. So the only thing that is left in here in this calculation is 2 over L times this integral from 0 to L over 4 sine squared of pi x over L. I think we have seen this integrals time and time again. At least we saw it 3 times today, or at least this formula involving the sine squared. So again, this, if you look few steps up, sine squared, wherever you like, it's given by in terms of the cosine root twice the argument, sine squared everywhere. So the identity now is worth remembering. Okay, so this is the identity that we're using. Cosine twice alpha is equal to minus sine squared of twice alpha. Sine squared of alpha. Okay, so sine squared by itself is just 1 minus cosine divided by 2. So this is basically 2 over L, the integral from 0 to L over 4 though, of divided by 2 of 1 minus cosine of 2 times pi times x over L dx. Okay, so that is basically what this whole thing means. Now the integral now is not 0 because we are not integrating from 0 to L. The integral has a finite value in here, so let's call this probability P 0 to L over 4. Okay, did they say L over 4? Yeah, L over 4. Okay, so basically it's a quarter of so if this is the box, this is how the box looks like. So if this is from 0 to L, and it's quarter of a length in here. Okay, so this is L over 4. So how probable the particle is going to be here versus how probable it's going to be here or here. This probability function is periodic, it's symmetrical, so if we calculate it in here, we're calculating it in there too, between 3/4 of an L and an L. So let's do that. First of all, these two cancels. So this probability between 0 to L over 4 is simply equal to the integral from 0 to L over 4 of dx, I mean 1 over L, I'm sorry, dx minus the integral over 1 over L, the integral from 0 to L over 4 of cosine of 2 pi x over L. This is just going to give me L over 2 times L, 1 over L, and that is L over 4, I'm sorry, L over 4 times dx, so that's basically the integration in here, minus 0, so if you care to write that. So the L and the L cancel, so this is going to be 0.25, okay? Minus 1 over L. Now if I integrate this one, the integral of a cosine is a sine, but I have to multiply by L and divide by 2 pi, and this is the integral between 0 and, I'm sorry, the sine of 2 pi x over L between 0 and L over 4. This number, the lower limit is 0, the upper limit is L over 4 times 2 pi, so it's going to be pi over 2 basically after the L is cancelled, which is 1. So this is the whole thing then. The L cancels the L, which is nice. We don't care about the size of the actual box. This is true no matter how big the size of the box is, the width of the box is. So this is 1/4 minus 1 over 2 pi times the sine of, again, x is L over 4 times 2 pi divided by L, and this is going to be pi over 2, and the sine of pi over 2 is just 1. So this is basically the answer to this whole probability. It should be less than 1. So we have 1/4 minus, it's going to be actually a lot less than even a quarter, so it's going to be a tiny number, 1 over 2 pi. Which is 0.0908, so it's going to be 9.1%. Okay, so this probability is about 9.1%. Let's look at the probability now for it between L over 4 and L over 2 in this region. Now this is closer to the center. Okay, how probable that is. So let's look at that. We're going to do the same thing actually. We're going to, up to this point, the boundaries of the integration change, that's all. Everything is going to be the same thing. Except the boundary, instead of from 0 to L over 4, it's going to be from L over 4 to L over 2. So, P from L over 4, I'm sorry, to L over 2 is going to be the, again, 1 over L, the integral from L over 2 to L over 4 of dx minus, again, 1 over L, the integral from keep on saying 0, L over 4 to L over 2, L over 2. Okay, hopefully I didn't make any mistakes in here. 2 pi times x over L dx. Yeah, I forgot a dx in here. I did. Hoping that no calc instructor is watching this. Okay, so this one is going to be again L over 4, because L over 2 minus L over 4 is going to be an L over 4. So this is going to be quarter again, minus 1 over L again is going to pull an L over 2 pi, so it's going to be an L over 2 pi L. The L cancel the L, but the integral now is going to be a sine again of the same stuff of 2 pi x over L, 2 pi x over L. Now L evaluated between L over 4 and L over 2. Well, when L over 2 first is going to be 2 times pi times L over 2, and I have an L in the denominator, and you cancel the L and the 2 and the 2, so this is going to be 0. The upper limit is going to be 0, and the lower limit is going to be again 2 times pi times L over 4 divided by L, and that just cancels that. This one is that. It's going to be 1. So I'll have a 1 minus 1 in here, 0 minus 1 in here, and I have a minus in there, so it's going to be a plus. So the probability is actually has the same numbers, except that instead of taking the difference between these two numbers, I'm adding these two numbers. Okay, 2 pi. So it's going to be minus minus, so it's going to be the same expression with the exception that now, come on, I'm adding this to a number, so the probability is going to be higher, of course. And that is exactly my point earlier about how quantum mechanical system, it's going to be 41% because it's giving me 40.9, 0.49, 0.049, 0.409, which is 41%. 41% is a lot bigger than 9%. So the probability of finding the particle anywhere near this middle in here, there is 40% chance of having it in here, 41% chance of having it in here, and 41% chance of having it in there. So it's an 82% chance of having it somewhere in here, and it's only 18% to be in the edges. Yeah, I mean 9% here and 9% there. Okay, so that is basically what this is saying, that the particle is most likely to be in the middle than to be in the edge, which is the opposite to what we see in a typical problem that we do in harmonic oscillator, for example. When we look at the probability of finding a classical particle, for example, near the edge, it's going to be more probable to be toward the end than toward the center. So again, I talked about that in lecture. So this is x naught for a harmonic oscillator. This is negative x naught for a harmonic oscillator. This is the position of equilibrium for the mass spring system. Obviously, as the particle is moving toward this one, it's going to slow down. So it's going to take more time getting reached this point. It stops completely when it reaches this point, and then it starts accelerating again. And it takes a long time in here doing those two things. Whereas in here, it's going to zoom by super fast with a maximum Vmax. Okay? So it's going to take the least amount of time. By the time it reaches this point again, it starts to slow down, and in doing so, it takes a long time, stops completely with v equal to 0, and then takes off again with the velocity gaining. So the acceleration starts to grow. I mean, the velocity starts to grow because the acceleration is at max in here. So it's going to start to grow until it reaches this point where it zooms back with the absolute value of Vmax again being the maximum value. So in this case, in classical mechanics, a particle, if you do its probability of finding it, for example, in the middle, it's going to be less than that of the edges. Okay? Whereas in quantum mechanics, the behavior is the opposite. Particles spend most of their time in the middle than in the edges. And this is true for the harmonic oscillator, true in this case too. So I mentioned that in the lecture, and I said that I would come back to it, and this is where we come back to it. Add the probabilities calculated in part 1 of our results. Okay, of course, if I add these probabilities, it's going to be 50% of the time on this side. I know I found 41% plus 9%, that's 50%. By symmetry, it's 50% on the other side. So the probabilities indeed add up to exactly 100, which is supposed to be 1. Okay? So that was the interpretation of the oh, I promised also problem 53. I know I did not mention that when I started with this thing. Did I say problem 53 in the beginning? Because I thought I mentioned it. Yeah, problem 53 also, I included it in here. It's one of the problems we're going to touch base with. So let's do problem 53. Problem 53 basically. Okay. Problem 3. Consider a one-dimensional lattice of carbon nuclei with interatomic spacing d equal to half a nanometer. So d, the distance between them, is about 0.5 nanometers, or 0.5 10 to the negative 9 meters, or 5 times 10 to the negative 10 meters, which is about 5 angstroms basically. Okay. The potential energy of one nucleus due to the electrostatic energy with its nearest numbers is given by, and they give you the expression for it, V. This is the potential energy, so probably I shouldn't use like the book is using in this problem. So it's actually U, because it says Q squared in the numerator. Okay, it has Q squared divided by 4 pi epsilon naught, not to confuse it with the electrical potential in this case. Okay, times 1 over d minus x plus 1 over d plus x. So this is basically how we're writing this energy. Okay, and Q is 6 times the charge of the electron. So this U then can be written as clearly Q squared over 4 pi epsilon squared. The common denominator in here is d minus x times d plus x, which is d squared minus x squared, and the numerator is going to be d plus x plus d minus x, which is 2d. Okay, so that is basically the expression in here for the potential. So I could write this potential, because I want us actually to do it, as Q squared times d over 2 pi epsilon naught times, okay, I'm going to put another d in there, so it's not a good idea to keep this d in the numerator, so I'm going to put a d squared in the denominator, so it's actually 1 over 1 minus x over d squared. Okay, so this looks more like an u naught, where u naught is equal to q squared over 2 pi epsilon naught times the distance. So this looks like an energy potential maximum. So u sub x then looks like just a dimensionless number, actually, u naught times a dimensionless number, which is 1 over 1 minus x over d. In other words, now the distances are expressed in terms of that lattice spacing d, or interatomic spacing d. Okay. Sketch the potential between x equal to negative d and x equal to positive d. Obviously, this is a function. When x goes to d, it's going to blow up, and on either side. Okay, and so basically between them, so this is negative d and this is positive d, and for x equal to 0, the potential is somewhere in here, is actually equal to exactly u naught, the one I wrote in there. Okay, and for x equals to going to d, I'm going to divide by a very tiny number on either side, so the number is going to grow basically exponential, not exponentially, yeah, it's going to grow with the power law. This is an asymptote. But this is how the potential looks like for this basically lattice of carbon. It's a one-dimensional carbon of lattice. Okay, this is the model that we have here. So we did that, sketched. At low energy, it's a good idea to put it in a calculator and see how it looks like, a graphing calculator. At low energy, the nucleus remains in its equilibrium, its equilibrium x equal to x0. So this is the equilibrium. This is the minimum energy in this case. Okay. Again, this is a quantum effect, so we know that this is how the quantum particles behave. Okay. And the potential energy is well approximated as a harmonic oscillator. Use the power series in Appendix B to express that. So basically, if you look at Appendix B, it's 1 over 1 plus epsilon is roughly equal to 1 minus epsilon, except in this case I have a minus in here, so it's going to be a plus in there. Okay? So that's it, because that quantity is tiny, so this is going to be u sub x is roughly equal to, in this approximation, as u naught times 1 plus x over d squared. Okay, dropping contribution in higher order, so we're neglecting any term of the order of x cubed and up. Actually, the next order term will be x to the power 4 or something like that. So okay, so we're neglecting higher order terms, and epsilon squared in this case they're of the order of, in this expression, I'm sorry, where we neglected the terms of the order of x to the power 4, namely x over d to the power 4. Okay? So in other words, the molecules in this case, or the atoms in this case, they're not bending too far in here. Okay? Actually, even if they do, it's not going to be too much, because there's a, it's like, this looks very close to an infinite well, actually. Dropping contributor higher order. C, what is, hold on, okay, somebody is knocking on the door, okay? Sorry about that disruption. Anyway, so basically, So we found, they ask us to, what is the spring constant? In this case, the spring constant is going to be just the coefficient basically of this potential. So the spring constant in this case is the coefficient of x squared. This looks like basically something which is the origin of the potential, in this case u naught, plus u naught times x squared over d squared. This term in this case is going to be 1/2 of kx squared. Okay, so this looks like 1/2 of k prime x squared is equal to u naught over d squared times x squared. So in this case, k prime then must be equal to 2 u naught over d squared. Okay, so if I plug in u naught again, the way I define it is q squared over 2 pi epsilon naught d. The d and the d squared will have d cubed in it. So k prime now looks like, and then I have the 2 in there, so it's going to be 2 times q squared, which is q squared. In this case, divided by, again there was a 2 in here, so I'm going to cancel that, pi epsilon naught, and then I have a d cubed now. Okay, so this is basically the expression that we ended up with in here. There was a 2 from the spring constant formula, and then you have, because this would be the potential energy of a spring, 1/2 of kx squared, but it's not, it's u naught over d squared x squared. This is basically just a shift in the energy. It's this amount only. So if I'm going to use the harmonic oscillator, this is basically the harmonic oscillator for x equal to 0 is 0. So we shift just the origin by that much. So this is the energy that we're shifting with the amount of this thing. So again, if we can express it in terms of E, because then we know that E is equal to Q is equal to 6E. So this is actually 36 E squared over pi epsilon naught times d cubed. We have d to be 5 times 10 to the negative 10 meters, and we have E to be equal to 1.6 10 to the negative 19 coulomb, and we have 1 over 4 pi epsilon naught equals to 9 times 10 to the power 9, basically SI. Okay, so in this case, of course, I don't need 1 over 4 pi, I just need 1 over pi epsilon naught, which means that I have to multiply that by 4. So it's 4 times 9 times 10 to the power 9 SI. Okay, and if I plug in the numbers in here, so we're going to get that k prime. So let's get the k prime in here. You're supposed to check my numbers, okay? And my work. You're not supposed to be watching. You're actually supposed to have a piece of paper and a pen, and you're doing everything I'm doing in here and checking and making sure I don't make mistakes. And if I do, please let me know so that we can correct these things, okay? So k prime is equal to 36 times e squared, which is, open parentheses, 1.602 times 10 to the negative 19. The whole thing is squared. Okay. Oh, I forgot to do something in here which is very important. Divide by no, keep it in SI, okay? Because we're looking for k prime in Newton per meter, okay? So let's keep it in here because we're looking for k prime in here. It's gonna end up with a unit basically of how many newtons is needed for this per meter, okay? Remember, we found 5900 for the previous k prime in another problem. So again, divided by, or actually multiplied by 4 times 9 times 10 to the power 9, 4 times 9 times 10 to the power 9, and the whole thing is divided by d cubed. Man, d cubed is huge. This is going to be a big number. Let's see here. D cubed. D is 5 times 10 to the power negative 10. The whole thing is cubed. Okay. Did I do it right? I'm not sure. We found 266. Please check the number. Okay, we found 200, which is typical of these things in here. K prime is 266 Newton per meter. Okay. Do we believe that? Do I believe that? So this is 10 to the negative 38, and this is 10 to the negative 30. So we have 10 to the negative 8. But don't forget I have 10 to the power 9. So 10 to the negative 8 and 10 to the power 9. So yeah, it is believable. It's a right number. Okay. So this is basically the value for the spring constant equivalent of this system. What is the energy of the classical ground state? Meaning U naught. Okay. U naught is just everything without a d, the other d squared in here. No, there is another factor of 2 also. So it's going to be q squared over 2 pi epsilon naught d. That was actually the energy that we shifted everything with. So U naught is equal to q squared over 2 pi epsilon naught d. 2 pi epsilon naught d. Okay. I'm going to keep this into, so this is going to be 36 e squared over, I'm going to multiply this by 2 again if you guys don't mind. And then I have 4 pi epsilon naught, because it's easier for me to know the value of that, times d. If I want to find this expression in terms of, this is going to be in joules by the way. If we want to find it in electron volt, we have to divide by another e in here. So that the formula then is straight out 2 times 36, which is 72, times 1.602, 10 to the negative 19. So the answer is going to be in electron volts, okay? Times 4 pi epsilon naught, which is 9 times 10 to the power 9. And the whole thing is divided by d. And d is 5 times 10 to the negative 10. Okay. It's 207.6 or 208 electron volts. A lot of energy to this shift in here, the energy. Okay. It doesn't mean in terms of spectroscopy what matters is this basically transitions between this energy levels. Okay, so this one doesn't participate in that. That means that this carbon is well anchored in that location, that's all. Okay. What is the energy? So, and what is the energy of the lowest energy photon emitted when this system transitioned between energy levels? Obviously, if you guys remember the expression for the harmonic oscillator for the energy, because now we're treating it as a harmonic oscillator basically. Okay. What is the energy levels for the harmonic oscillator? They are spaced by n. They are all equally spaced in this case between n. So the lowest transition is between the next two levels basically. Okay? Because if I have two levels, they're going to be spaced by basically the next two levels and so on and so forth. So I need to find again. Did they give us the mass in here or what? Because we need the wavelength. Are we going to use the mass of the carbon nuclei? Because we need their mass to find omega. Okay, because all we know right now is K prime. So carbon is 12. Okay, so it's 12 times basically. So we need omega, and omega in this case is going to be equal to square root of K prime over the mass of the carbon, in this case nuclei. And that is going to be square root of this number that we found earlier, K prime, over the mass of the carbon, which is 12 times 1.67 times 10 to the negative 27 kilograms. Because I am using roughly the mass of that of a proton. So omega naught, basically, this is omega naught, is going to be square root of 266, did we say 266, divided by that number. 266 divided by 12 times 1.67 times 10 to the negative 27 kilogram. So this is square root of k over m basically, and so this is going to be square root of 266. It's going to be a big number, of course, divided by, but don't forget we're going to multiply it by h bar to get the actual energy level. So, and don't forget we're going to divide that by electron volt too, to get everything in proper electron volts. So again, divided by 12 times 1.67 times 10 to the negative 27, and this is under the square root, of course, and this gave me 1.15 times 10 to the positive 14 hertz. Of course it's going to be that high. Okay, I'm sorry, radians per second. This is an omega, not the frequency. Okay, so we have omega. So now all we have to do is the energy gap between them, if you remember from the lecture, is n1/2 times h bar omega. This is one level. The next level is going to be n plus 1 plus 1/2 times h bar omega. So if I subtract the 2, this must give me the energy gap between these two next levels. So it's going to be 1, basically it's going to be h bar omega. Okay, so delta E. We should have found the frequency because this is HF actually, or if you wish, H, which is 6.626 times 10 to the negative 34 divided by 2 pi times this number that we found earlier for omega, which is 1.15 times 10 to the power 14. However, I'm going to divide it by 1.6 times 10 to the negative 19 to get to the electron volts. So let's take this number now and multiply that by 6.626 10 to the negative 34, and divide that by, open parentheses, 2 times pi times 1.602 10 to the negative 19. So the answer is going to be in electron volts, and it's 0.0758 electron volt. It's very tiny basically. This is the energy, basically the difference in between energy levels. So it's 0.07878 or 758. Okay, electron volt, or if you wish, 76 micro electron volt. Okay, oh man, okay, I'll leave it as is. Okay, I don't care. That's good enough. Okay, that's good enough for this thing. Hopefully you guys. What is the wavelength corresponding to this radiation? Well, since we found omega, now we should be able to find lambda, since we can find f from this one. Remember, we have omega equals to how should I say it? Okay, c. It's going to be equal to lambda f. In this case, lambda is c over f, and it's going to be 2 pi c over omega. Okay, so it's going to be 2 times pi times 3 times 10 to the power 8 divided by omega, and omega is that big number that we found earlier, 10 to the power 14. So it's going to be 1.15 times 10 to the power 14. Okay, so let's find the wavelength in here now, and that's going to be the last part of this problem. It's a long problem. Okay, so we have 2 times pi times 3 times 10 to the power 8. The whole thing is divided by omega. Come on, omega. You guys don't know this program, Microsoft, basically mathematics. It's a useful program. It's a calculator really. All you have to do is double click on a value and it's going to give you that. It's 1.6 10 to the negative 5, or actually 16 micrometers. So lambda is 16 micrometers. Okay, 16.3 if you want to care about the number in there. Okay, it's not in the visible light. This is well in the infrared too. So this is very, very long wavelength. Okay. So again, so this is problem 53. Problem 60, which is going to be the last problem in this set. I know this is unusually more problems in here, so I really want you guys to emphasize on this chapter because of the exam that is coming, so hopefully you guys will be ready for it. So 60, problem 60 is a data problem. Okay, so as an intern at the research facility lab, you study the transmission of electrons through a potential barrier. You know the height of the potential barrier is equal to 8 electron volts. So we know U naught is equal to 8 electron volts, okay? But must measure the width L, so we don't know what L is. Okay? When you measure the tunneling probability T as a function of the energy E of the electron, you get the results shown in the table. So basically they give you E as a function. E goes from 4 all the way to 7.6. It cannot be, actually, if it needs it to tunnel, it cannot be more than 8. So E in electron volt is given, and it starts with a value of 4, and it goes all the way to 7.6 electron volts. And in this case, T, the probability starts, of course, to be tiny, of 2.4 10 to the negative 6, and reach almost very sizable number, 0.8% or 8.1 times 10 to the negative 3. Okay, so there are numbers in between. For each value of E, calculate the quantity G. So we're supposed to find G. Okay, remember G is supposed to be, the formula for it is supposed to be 16 times E over U naught. G is equal to 16 times E over U naught times 1 minus E over U naught. Since we have E and we have E for different values of E in here, and we have U naught 8, so we can use this formula and find it. Okay, that's one thing. Now graph ln. No, if we need to find kappa also. Kappa, they give us the what is M? As an intern research lab, transmission of electrons. So we know the mass of that of the electron, so we can find kappa now. So kappa is going to be square root of 2m. M is that of the electron, times the energy gap, which is actually U naught minus E times divided by H bar. Okay, so this is the expression that we have found for the actually this is the first problem we started with. Okay, so if you are not familiar with this one, I want you guys to come back to this problem in here. Okay, so 2m divided by the energy gap divided by H bar, and then the square root, of course, for two terms. Okay, so this is kappa. So assume that we can find kappa in here too. And finally, graph ln of T over G. Okay, and versus kappa, explain why your data plotted the way that it is fall as a straight line. Okay, if everything does correctly, because we know that T is equal to G times exponential of minus 2 times kappa L. Okay, so if I take the ln of T over G, this simply becomes minus 2 kappa L. Okay, the only thing is I don't know exactly if the ln of in Excel is going to give me an ln or something else. Of course, if this is y and this is x, this is going to be a line, okay, that goes like this, the slope of which is going to be exactly equal to 2l. Okay, so that's basically why we're expecting this to be a line. Okay, use the slope of the function best fit to find L. So if we find the slope we're going to just divide it by 2, and that is L that we need to find. Okay, so L is going to end up being just the slope over 2. So let me start this problem with Excel. Let me get Excel going. Okay, so we have Excel now, and let's start plotting stuff in here. So we have E first, and E is given to be 4, 5, 6, 7, and then 7.6. Okay, we need T now. T is a probability, so it's going to be 2.4 times E 10 to the negative 6, okay, 1.5 E 10 to the negative 5, okay, and then we have 1.2 E to the negative 4, and then 0.0013, okay, and 0.0081. Okay, so these are the numbers they gave us in here, and for the different values that we have in there for T. And E is an electron volt, and we know what U naught is, so we need the value of G first. G equals to 16 times the ratio of this number divided by 8. So we're going to multiply it, so let's multiply that right now, okay, times 1 minus this number divided by 8. The whole thing is divided by 8, okay? The whole thing is divided by 8 one more time, because 8 we divided by 8 times 1 minus. Okay, so this is the formula, and let's copy this and paste it everywhere. So this is G, okay, the values of G. And then we want also to find kappa. Kappa for the electron is, the mass of the electron is 1.6 10 to the negative 19. So I'm going to write kappa in here, okay, and kappa is equal to, again, equals to square root of, open parentheses, 2 times the mass of the electron, which is 9.1 times 10 to the negative, Excel, you have to be very careful with this negative stuff here, negative 31, okay, times the gap in the energy. So this thing has to be in joule now, okay? We need it in joule. Yeah, because each bar is in joule. Times the difference in energy, and the difference in energy is between 8 minus this cell, okay, and this one multiplied by 1.602 times 10 to the power negative 19, okay, and close the square root now. I forgot to multiply by 2 pi. No, I don't need to. Yeah, we need to divide by each bar now. Divide by, open parenthesis, 6.26 times 10 to the negative 34. Okay, probably should have used the constants instead to make all of these things easier to write and read. Okay, divided by, open parentheses, 2 times, and Excel has this function called pi for pi. Okay, So this is kappa. Again, it's a big number, supposed to be a big number. Control C and then paste it everywhere. Okay, so these are the different values of kappa. Okay, and now we're going to take the ln of T over G. Okay, we're going to find T first, and T is here, and kappa is here, and right, just, I'm sorry, 10 over G, which is 10, this one, T over G. So we're going to find in here the ln is equal to, let me just test this ln business because I'm not confident that the ln, so equal to ln of 2.72. It should be slightly more than 1 if it is just a natural, it is a natural log ln. Okay, so equals to ln of T over G. T over G. Control C and paste it. Okay. So we're going to graph this function ln of T over G as a function of kappa. Okay, so this should be my independent variable and the other one should be my dependent variable. So they're straight out like this. Okay, my independent variable is actually kappa and my dependent variable is this ratio of the log. Okay, the ln of the ratio. So I'm going to insert now this line, and as expected it is actually a let me move it to its own chart. Move to chart. Okay, as expected it is a line that is decreasing exactly how it's supposed to be. So we're going to go in here and more options, and we're going to do a linear, which is fine, and we're going to display the equation, and we're going to actually have that. So in this case the y-intercept, I mean not the y-intercept, the slope, which we will need in here, is negative as expected, and it's 1 times e 10 to the negative 9, and 10 to the negative 9, that is actually 2l, I mean L over 2. So it's actually of the order of a nanometer, exactly how we're supposed to have it in here. Okay, so just in case, again, let me look at my notes again quickly. L should be the slope over 2. Okay, up here the slope in here is negative, so we have to take the slope with a negative sign. Okay, because we have this negative business in here that we have to fix. So it's going to be minus slope because we're looking for a length in here. So let's quickly do that in here. So L is going to be equal to minus slope of, and we're going to take the y-axis, which is this one, okay, comma the x-axis, which is this one, and that is, the whole thing is just divided by 2. According to this number, it's 6.98 times 10 to the negative 10 English 10 basically meters, or 0.7 micrometer. So L is 0.7 micrometer. Okay, 0.698 or something like that. I don't recall that number. 6.98. So to be more accurate, nanometer. 0.698 nanometer. Okay, or 6.98 times 10 to the negative 10 meters. Okay, and everything is in SI. Everything is supposed to have me the values as I expect them. Okay, use the slope of the best fit graph line to calculate AL. So this is a typical number for the for materials in here. So So the barrier in this case is of the proper order 2 of magnitude where it's supposed to be. Anyway, these are the problems from this chapter. And there are quite a few number of them, so I needed to touch base with the lecture. There are 1, 2, 3, 4, 5, and 6 problems. And hopefully you guys learned something from them. Please do not rely on my calculations or what I did. Do that on your own to learn from them. Thank you.